Hey guys, so today we're going to do a couple of things via video. One is to review your quiz, so you should have received that before the playing of this video. Make sure you do have that out. We are going to go over the problem section. With regards to the multiple choice, there's plenty of classmates that probably got one right that you didn't, or at least you can discuss it together much more easily. So I'm not going to go through the multiple choice part, but I am going to go over all the problems. Typically, if you got those wrong or got one of them wrong, there was some key kind of things that seem to show up repetitively on those that missed those. So we'll talk about those when we get to that. Then the second part is just to go over stoichiometry in general and do a few practice problems before I let you work on the rest of your worksheet. I would encourage you, I know some of you are probably feeling really confident when we get to the stoichiometry based on what you've looked at this week, that you can just ignore the video, ignore the lecture, and just start working. But let me encourage you, just for once, like, humor me and stick with me. I'll try to make it as painless and quickly done as possible so that you have time to work. I know that your time is valuable, as is mine. Quick update for me. I am getting much better, and we will see what the weekend holds in order to figure out. Hopefully that I'll be with y'all next week. But again, we're just trying to get some last minute kinks figured out to see how I do off medicine as well as just stamina from the standpoint of trying to do something for 8 hours that I haven't been doing in over a month. So with that, we are going to skip over to the quiz, and we'll get through that really quickly. All right, so for the first couple of questions when it comes to those that we're trying to work on. The first one is a mole conversion problem. That's where we should be using that Y diagram. I totally misspelled that. We should be using the Y diagram. You get the idea, right? Of where we can go from various units to various units. Let's see if something, here we go. I was like, I knew something was missing. For this one, we are given 3.5 liters of sulfur dioxide. So if you've got liters, if we're thinking about that Y diagram, we want to go from the area of liters of gas or volume of gas at STP. The only thing we can do from liters is go to moles, and that's using that 22.4. Some people had an issue with memorizing that number. Some people had an issue with knowing how to write formulas. That's still a problem, not good. So once we get to moles, then from moles we can go to grams, which is what mass is asking us for. And so the mass of sulfur dioxide is using that molar mass of grams per 1 mole. And when we solve for that, we get 10 grams. Now with that, the one thing that threw some people a loop, and again, sig figs was only a point off, but was significant figures. We always have to go back to our original given number value, or number given in the problem. That is our measurement value that we have, and that's where our precision comes in. That tells us the instrument that we had could only tell us for certain that it was 3 liters and estimated that it was 3.5 liters. But it might have been 3.4, it might have been 3.6, we're just somewhere in there close to 3.5. But if we had had a beaker or a volumetric flask or an all those different things, a graduated cylinder that we could measure our volume with, if it was more precise, if it gave us more details of significance, then our answer could be more precise as well. But since there's only 2 significant figures, the 3 and the 5, our answer can only have 2 significant figures. There's a couple of ways that you can do this. If you put a decimal after the 0, then that 0 becomes significant. Okay, so it needs to have 2, the 1 and the 0. If there's no decimal there, then you're only saying you know to the tens place how good it is. The decimal there says, hey, I know to the tens and the ones how good I am with regards to that precision. Or I could have written it in scientific notation. And I know all of you like to not deal with scientific notation, but it is a secondary way that you can write correctly with significant figures how many grams of sulfur dioxide there is. So again, big things that messed people up on this problem. One was not knowing to use the Y diagram properly. Two was not having the right formula or molar mass for sulfur dioxide, which meant that typically you wrote the wrong formula. Sulfur dioxide is a covalent molecule, so that tells us there's one sulfur, there's no prefix in front of sulfur. And then the di tells us that there's two oxygens. There was a few people that made, when you get the quiz back, you'll be like, oh my goodness, that was a silly mistake. And that happens sometimes when you're taking quizzes. Just be real careful when you're looking at your substances of what they are. So that kind of helps you figure out number 11, and you can see where your right answer is. For number 12, most people got this right. Again, going back to formulas, if you knew how to write lithium phosphate, 88888, tells us that it's a polyatomic ion. It was pretty much an easy peasy on that. There were a few people that flipped the percent. If you're thinking about any kind of percentage, whether that's the percentage for your quiz that you just made, you'll see that I have a certain number out of 50. So it tells you how many, that's the number that you got right out of how many were possible. It's the same thing when you're doing any kind of percentages. It's the part you're looking for, in our case for a quiz, the part you got right, divided by how much total there is. And for this, it's that formula mass of the entire substance times 100 is going to give you a percentage. So if you wrote the formula correctly, you got Li3PO4. It was asking for how much lithium is in that. So what's the percentage of lithium? Lithium is, when there are 3 of them, it's 20.823 divided by 115-ish, multiplied by 100, 17.98. And depending upon which numbers you used, you might have gone to 5 sig figs, or you might have just done 4, depending on where you went. Typically I accepted both of those. If you only put 2 sig figs or didn't include those decimals, you might have gotten 1 point off. But like I said, most people got this one right. Again, if you looked at that formula and knew that it was lithium phosphate, everybody, for the most part, got the how to do it correctly. Here's where we ran into a gamut of, oh my goodness, you should have seen all the different answers I got. It was quite interesting. So this is the empirical formula, and I don't really know what it is about empirical formulas that seem to always like mess with people's minds or something. I don't know. It's like a black hole of craziness. But anyway, if you're trying to figure out the empirical formula, you're trying to figure out the lowest ratio of elements to each other in a compound. For this question, it says that it had 79% carbon, about 5.5% hydrogen, and 15-ish% nitrogen. When you're given percentages, you can automatically make this assumption that you have a 100-gram sample. If you have a 100-gram sample, then your percentages become the masses of those elements. And so you can utilize that mass number. Let me get all these little nice little, there we go, animations going. You can utilize, those mass numbers to then determine what your formula actually is. But we cannot use mass. Mass is not comparable because the mass of, if you think back to your bean lab where you had all different kind of beans and popcorn, okay, you might have had 25 kernels of popcorn and that was a PCU, and that was 5 grams, but if we go and get kidney beans or we go and get black-eyed peas, it's definitely not going to be the same number of beans that mass 5 grams, and so there's not an equivalence of using mass. Moles, though, can be compared to each other. And so when we think about doing any kind of formula, we have to have everything in moles. Moles, 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 moles. Grams cannot be used to compare anything. Okay, they're not comparative. So in order for us to do that, the only way we can get to moles of any of these substances is to use the molar mass. So grams per mole of carbon, 12.01 per 1 mole. And it's flipped because we're dividing grams by grams to get to moles. So we do that for each of those. You're going to get a mole number for each of those elements. Moles are not ratios though. And we've got decimals in addition to that. But this is not your mole ratio. What you have to do in order to do this is to actually divide by the by the least mole number that you're given when you're looking at those comparisons. So in this case, it's 1.098. Now some people got to this step and said, oh, let's just say that's about 6 and that's about 5 and that's about 1, which is true in this case, but you didn't show me the work of why that actually is true. If this had been 1.5, that wouldn't have worked. Not to mention that really should have been like 7, which still would have given you the right answer. So when you have the moles, and that's another reason why utilizing the unit and the substance helps you know you're not there yet. We've got to do that second step of getting rid of the unit because we just want a value that shows us the full ratio. And so in order to do that, we want to divide all of our elements by the element with the least number of moles. Because what this is telling you is, say, if I've got 15 grams, then that's about 1 mole of nitrogen. That's not telling you the ratio of nitrogen to hydrogen and nitrogen to carbon. It's just telling you how many moles you have. But you can figure it out by dividing by the least number of moles. So when we do that, we get about 6, about 5, and about 1. These are going to be estimates, and as long as it's not 6.5 or 6.33 or 6.67 or 6.75, some really off number that's not close to a whole number, then you can simply utilize those ratio values. Now if it was 6.5, then you'd have to double everything, or if it was 5.33, then you multiply it all by 3. Those can be things that throw a kink and make a step 3 with regards to figuring out empirical formulas. But luckily we were not. I wasn't trying to trick you on this. I just wanted to see if you could do it. And so your overall empirical formula was C6H5N. And 1 is understood because you wouldn't have an N there if you didn't have at least one of those. So that is what that number 13 really needed with regards to the steps that you had to do, what it was that was expected to be seen on the sheet, and to get that right answer. So C6H5N. Just so you know, I will post this on YouTube, but just wanted you to have it today. And then the last one, of course, if you didn't get 13 right, 14 became a little bit of a problem. The good news is it's only counted 4 points. I really should check my work before I start recording. So find the molecular formula. So I need a formula here for that compound talked about in number 13 if the molar mass is 273.36 grams per mole. Okay, so define the molecular formula when you were given a molar mass. There's a very specific, very quick, most of y'all did so much extra work. You still got to the same answer, and that's perfectly fine, but I could have saved you a lot of time, and actually I tried to when I actually told you how to do this the first go around. But I realized that most of you are probably looking at the videos and textbook and stuff when going through all of it. Both ways work. One's just a lot quicker. And some you may have just been using your skills of deduction and algebra. It all works. So the quick and easy. If you take the molecular molar mass, okay, that's going to be given to you in the problem, 273, and the empirical molar mass, you're going to have to calculate that once you get the empirical formula. When you divide those two, that's going to be the multiplier that you use in order to determine your molecular formula. So if I knew my empirical formula from question 13 was C6H5N, and I get that that's where a lot of people like, they didn't know if this formula was right, so they wanted to use a different method, perfectly fine. But this is the quick one. So I plug in to find my molar mass. The empirical molar mass is 91.11. So I take the 273 in my problem, the 91, I just calculated it. I divide that, and that gives me approximately 3. Well, that tells me that the molecular formula is 3 times larger than the empirical. So I multiply 6 times 3, 5 times 3, 1 times 3, and I'm given the empirical formula, or sorry, the molecular formula from the empirical formula. And that's a real quick and easy way to do it. Now, for some people, it was one of those, I don't know if I got 13 right. Let's see if there's something I can figure out. And yes, there is stuff that you can figure out because this gram per mole is still really important. So if I knew that I had 273 in the molar mass, and I go back up to that other problem, and I see that that's 79%, the percentages aren't going to change no matter what the formula is. It's just this empirical formula is a shrunken down lowest common multiplier formula of the molecular formula. So if I take the percentages and then I use the molar masses, then it's going to give me the same number, or an approximation of that number. And that's a perfectly good way to do it, especially if you're not really sure you got the other one right. But when you see this, if you got this one right, you should have been able to go back to 13 and fixed it. If you had some thought process, if you'd taken your time and been able to do that. And some of you may have done that in that you fixed 14 first and then went back and was like, light bulb, let me figure out the rest. So those are those problems in the quiz. Some people did really, really good. Some people did not, whether that's a matter of how much you studied or you just are not getting this. That would be something for you to figure out. For those not getting it, let me recommend a few things. One, practice, practice, practice. You're like, well, I don't know what to practice. Well, go back and look at the videos that are on YouTube. When they get to a practice problem, stop it when you see it and then actually write down what you know how to do. It's not just enough to write it down. That's a good starting point when they do it. But then if you can do it yourself and then see if you're matching up to what they're doing, that's a better lesson on whether or not you're actually understanding it or not. So the other thing that hopefully you have in front of you is the stoichiometry packets, 2 pages. The first is like, oh my goodness, that's a lot of stuff and I don't have to write anything down. Yes, you're welcome. I'm just going to walk you through really quickly the basics of stoichiometry. You've heard this pretty much Wednesday and Thursday of this week on videos, but you know, sometimes when I say it, apparently it makes more sense, probably because you're actually having to watch it. Anyway, let's jump over to stoichiometry. Sorry. I'm going to give you just a second to make sure you do have that out in front of you. So it's the 2 pages that's the unit on stoichiometry. You'll see tables and charts and helpful reminders, just things that we're going to go through really fast. And then we'll get to some practice problems guiding you through what's going on in stoichiometry. Stoichiometry, really big word that basically just means that we're doing quantitative math in regards to chemical equations. So all that stuff in the fall semester, well not all, but majority of stuff in the fall semester that I kept saying over and over again, you got to know how to do this, you got to know how to do this, you got to know how to do this, because when we get to the spring, it's going to be really important. Well, we're here. We have met that point. So writing formulas, balancing equations, predicting products, all that stuff. Yep, we're here, because now we're going to add math to it. And so that's where, if you are having trouble or difficulty with the fall semester stuff, we've now just basically dumped a load of not fun on top of all of that. So it's really important that if you're still struggling with the fall semester concepts, you know, it's going to be some weekends, some extra work, and I get that everybody's busy and everybody has schedules and all that fun stuff, but the math is just not going to make any sense if you are having to spend so much time on the old stuff. that's my plug. All right, so let's think back to what we're talking about when we're looking at chemical formulas. That's just the basics of all of this. So if we have H2O, okay, that means we have one molecule of water. Sorry, I'm trying to get through all these. We have one molecule of water. There's 2 hydrogens and 1 oxygen. That's what H2O means. If I say I have 2 H2O, then that means that I have 2 molecules of water. There's 2 hydrogens and an oxygen, 2 hydrogens and an oxygen. So there's a total of 4 hydrogens and 2 atoms of oxygen. If, though, I say I have H2O2, okay, the 2's in a different spot. Here we still have 2, but now we have 2 O's. That's saying I have 1 molecule of hydrogen peroxide. So there's 2 oxygens combined to each other, as well as 2 hydrogens that are stuck on each end. It's really important to make sure that what you're writing is understood so that you understand what each formula represents. Same thing is true when we're balancing equations. So let's say we have hydrogen and chlorine making hydrochloric acid. When I look at this, this is not balanced. This has 2 hydrogens, 2 chlorines, and 1 HCl. We're not having a nice balance here if we're thinking about a sea salt. So the only way that we can do that, let me get through, is to change our equation to show that we need 2 HCl's. That gives the H to the H, and the H to the H, and the Cl to the Cl, the Cl to the Cl. So everybody has a partner from reactants to products. And that's important because the law of conservation of matter says that we can't create or destroy mass or matter or anything. We're not God. We don't have that capability. Everything that was in existence from the time of creation up until now is just being recycled. And I know that can be kind of weird if you think through it, but there is no new atoms. They're all here. They're just being reused and reconfigured, put together in different ways. And so when we think about that, we have to make sure that when we're writing information down that we have those things balanced, because whatever equation we're actually writing, this stuff actually happens. When we take hydrogen and chlorine gases and we combine them together, it's going to make hydrochloric acid. It just is the process that happens. And so if we want to see hydrochloric acid made, then we've got to put those 2 gases together. So this is just a funny, I know it's kind of silly and stupid. It's not my invention, but I thought it was cute. So welcome to Mole Island. Those are funny. Those are really not even moles, which makes it even funnier. On Mole Island, as you know, we've already talked about this multiple times. There's really kind of 3 areas that moles can bridge us to other things. The mole can bridge us to volume, the mole can bridge us to mass, and the mole can bridge us to particles or representative particles of a substance. And that is important because the mole is the thing that we can use to compare different substances. It's apples to apples instead of apples to oranges. So, I'll just stay here. In that first part of your note sheet, you'll see that it talks about, for stoichiometry, what all things can we do with it? Well, basically, there's a lot of different things we can do with it. We can determine how much product is made or how much product is needed. If we know a certain amount of reactant, we can figure out how much other reactant we need in order for a certain amount of product to be made. Or just what those 2 things, how those ratios are going to work. We can also figure out how much reactant we need if we need to make a certain amount of product. And so all of those different things based on reactants and products can be done based on stoichiometry. So it really is a helpful quantitative way for us to see what's going on in chemical reactions. So thinking to the island, and this is just to try and help you kind of visualize if we're thinking about an island. The M would be our mass mountain, the volume or our liters could be liter lagoon, and our particles could be the particle place. And so anywhere on the island that we're trying to go, or we're starting from, so if we're starting from the mountain and we want to go to a different lagoon because it's from a different substance, we can utilize the island diagram to get us there. This is basically the Y chart doubled. And the reason it's doubled is because of mole island, which is those mole ratios that you did on Monday. The mole ratio is the key to being able to go from the known to the unknown. And so having that visual in front of you can oftentimes help, no different than the Y diagram, in making sure that you're following the right path to get from one place to the other. Oh, those silly things. Okay, so again, when we're thinking about that, and this is on your worksheet, from mass to mole, no different than if we were just utilizing this half. Okay, that's your molar mass, that's your molar volume, or sorry, your volume, and this is your Avogadro's number. Same thing on the blue side. The difference is to go from green to blue, we need to use the coefficients in a balanced chemical equation. If we can't balance an equation, then we can't get from moles of the known to moles of the unknown. And if the chemical equation won't balance, it's probably because we haven't written the formulas right. So again, thinking back to what was so important about fall semester, that's why I kept saying it over and over again like a broken record, that you have to know how to do this stuff. So this is what's on your worksheet. Again, it's just letting you see how you can move from one place to the other. Again, following those lines is still important. I can't go from particles of one substance to particles of another substance in one quick step. I have to go through the mole in order to get there. As long as you follow the lines, you're going to be at least setting it up correctly. And then from there, it's understanding formulas and when to divide and when to multiply. If we think about stoichiometry, we always usually come back to this idea of cooking. Chemistry is cooking, or cooking is chemistry, whichever way you want to say it. So if I wanted to make chocolate chip cookies, I have a recipe here on the screen. If I have 5 cookies, how many cookies, if I have 5 eggs, how many cookies can I make? So in our brains, we automatically look to our recipe. We see we have 2 eggs that would make 5 dozen cookies. I have 5 eggs, so the maximum amount of batches I can make is 2 using those 4 eggs. So I could make 2 batches, which would give me, instead of 5 dozen, it would give me 10 dozen. That's stoichiometry. The thing is, these are all mole ratios. Okay, this recipe is mole ratios. When we start looking at grams of things, again, like I talked about in the quiz review, you have to get to moles first in order to be able to compare them. So if I have 5 eggs, there's 2 eggs for every 5 dozen cookies. Of course, in all honesty, I couldn't really make 12.5 dozen cookies because, I mean, technically I could. Ideally, the eggs are going to run out, but if we're just looking at the overall, we look at that mole ratio, and we could get the 12.5. We really know we're only going to get 10 because you can't really put one. I mean, you can, but let me just tell you, don't mess with recipes. Okay, if the recipe calls to do it one way, just do it that way. Don't half it, don't double it. It just makes a mess. So you're only going to get 2 batches of cookies, so really you're going to be limited by that. We'll talk a lot about that next week with regards to limiting and excess reactants. But ideally, if we had 5 eggs and it's 5 dozen for every 2 eggs, we should be able to make 12.5 dozen cookies. But knowing that we don't really need to half this recipe, we'll know that we're really only going to make 10. So when we're thinking about that, it really, so how many cookies? That'd be 150. Anyway, going on. Stoichiometry, the real part. So it is based on that mole ratio because the mass relationships can't really be compared, although there is a relationship between those in a chemical reaction. But the mole ratio is the part that we can compare. It's indicated by the coefficients in the balanced chemical equation. So if I'm looking at the making of magnesium oxide, there's a 2 to 1 to 2 ratio. That gets me from how much magnesium I need versus oxygen to make the magnesium oxide. So this is like the most important slide. If you don't write anything else down or don't go back and pull this out again, this is important. How do you do stoichiometry? The first thing that you have to do is write a balanced chemical equation, which means you have to write formulas correctly. I know, I'm sorry. Then you want to identify the known and the unknown that are given in the problem. So you're going to be given a word problem. It may tell you certain parts. It might give you all the substances. It might assume that you know how to write products, or that if something's missing, you can go, oh, wait a minute, I don't have all my atoms here. I can't, I'm not God. I'm not going to destroy things or create things. But then you want to look at the problem and figure out what's known and what's unknown. You'll line up your conversion factors. So this is setting up the dimensional analysis of the problem. The mole ratio is going to be moles to moles. The molar mass, moles to grams. The molar volume would be moles to liters of gas. This again is at STP. The core step, though, in all stoichiometric problems is going to be the moles to moles. You cannot get from grams of one substance or liters of one substance to grams or liters of another substance, or even particles of either of those substances without the moles. And because you're going from moles of one substance to moles of another substance, you have to have those coefficients in the balanced chemical equation to do that. That is your core step. Really, really important. Really, really important. And then you want to check your answer. So when it comes to those steps, there's really only 4. Now, there's a lot of kind of intermediate steps when you're thinking about what's happening in that, but those are really your 4 steps when it comes to stoichiometry. So it's not really bad. Most students have issues with this only because of having to do all the work. They would rather just type it all in their calculator and be done, not writing anything down, but that can get you into trouble because you're multiplying and dividing, and it depends on which way you're going as to what operation of math you're doing. Okay, so hopefully you have those. If not, you can pause the video. Alright, so this is a sample problem that's not on your worksheet, but I just wanted to go through one where you're just watching instead of trying to write and watch. So in this one, how many grams of potassium chlorate are required to produce 9 liters of oxygen at STP? So we have to think about what is actually happening here in this problem. We know that we have KClO3, and if it's required, then that's a good indication that this is going to be a reactant. And then to produce, that would tell you that oxygen is a product. Now, if we think about that, there's only 2 things that we know, this KClO3 and this O2. So there has to be something else left, and that would be your KCl. Decomposition reactions are not ones that I expect you to know all the products for. I would give you this equation. It wouldn't be balanced, of course, but in thinking through that, it is decent in order to figure out what exactly is happening. So we now have our balanced chemical equation. What we know is that there's 9 liters of oxygen. What we want to find are the grams of KClO3. And we know that it's at STP, which is important for us to be able to use that volume of gas. So we start with what we're given. We set up our conversion factors. And how to do that for liters, the only thing in our Y chart or in our island diagram that we can go to from liters is to go from liters of oxygen to moles of oxygen. It is critical that you put what the substance is, because what's going to end up happening is if you just put moles here and forget oxygen, you're going to miss that middle step, because you're going, oh, I'm already at moles, I can go to grams. No, you can't. You can't go to moles of oxygen, from moles of oxygen to grams of potassium chlorate. You're missing a step. So please, imperatively please, write down the substance. I know it may be like 5 more letters, or it may be 2 more letters and numbers. I get it, but trust me, in the end, when you're going back to check, if you have units and you have substances, it's going to be much easier to make sure you haven't missed a step or messed up. So we have 9 liters of oxygen. The only thing we can go to is moles of oxygen using our Y island chart diagram. Once we have moles of oxygen, at that point we can use this mole ratio, and we could go to moles of potassium chlorate, we could go to moles of potassium chloride, anything within that balanced chemical equation. Because it is a ratio, we can compare the different substances. So to get rid of this moles of oxygen, we have to use the mole ratio of what we have to what we want. It's a 2 to 3 ratio, and then we have to get the molar mass of the potassium chlorate. Do the math. Again, if you want to multiply across the top, get an answer, multiply across the bottom, get an answer, divide the two, or if you just want to treat each one like fractions, whatever floats your boat. As long as you're making sure that top stuff is multiplied, bottom stuff is divided, you should all get the right answer, which gives us this 32.8 grams of potassium chlorate. We always want to go back at the end to make sure we're rounding the correct number of sig figs. 9.00. The decimal says, hey, y'all are significant. This is a nice piece of equipment instead of a junky little beaker that doesn't tell us a whole lot of information. And so that gives us that final answer in 3 sig figs. Okay, so that's just one, again, for you to listen to and think through what is happening, what you're given, what you want, how you get there. Look for your sig figs in your answer. Okay, so this is on the back of your worksheet, and I was nice enough to go ahead and balance it for you because I want us to really focus right now on the stoic part. You'll have plenty of time to go back and put it all together, but right now I just want to make sure we could look at the stoichiometry part. So we have this titanium dioxide and chlorine and carbon reacting together to make carbon dioxide, carbon monoxide, and titanium 4 chloride. And so it wants to know how many moles of chlorine will react with 4.55 moles of carbon. When we're looking at our island diagram or thinking through just the problem itself, we have to think we're given moles of carbon, we're wanting moles of chlorine. So this is really just that mole to mole conversion. We're just looking at the ratio. So has carbon, we have 3 moles of carbon. And how many moles of chlorine? We've got 4 moles of chlorine. So we're looking at the ratio of this really 4 to 3 because this is what we want and this is what we're given. So in writing that down, we can look to see this is what we want, this is what we're given. If we're thinking about the island diagram, the carbon we're starting and the chlorine we're going to. So on the island we're starting at moles and we're ending at moles. So this is just one step. Okay, this is the process that you can follow if you think through your island diagram. So this is what we're looking for. This is the final answer that we want. We want moles of chlorine. What we're given is 4.55 moles of carbon. We're going to set up our conversion factors. There are 3 moles of carbon. There are 4 moles of chlorine. What we're trying to get rid of goes on the bottom. What we're trying to go to goes on the top. The moles of carbon cancel out, and we get our answer. 6.07 is 3 sig figs. 4.55 is also 3 sig figs. So we know that we have not only our final answer, we have a calculated answer, we also have a final answer. Oh, there's a 2 missing right there. Sorry. It's been a long day. Alright, so again, if it needs to pause, that's fine. Otherwise, I'm going on. Alright, so the next question is kind of a continuation of that. We still have that 4.55 moles of carbon, but it wants to know now how many grams of titanium 4 oxide or titanium dioxide, depends on which place you're going with it. How much of this is going to react with this other stuff? Okay, so there is going to be a certain amount that can react based on this ratio. No different than thinking about your eggs, and let's say you had your flour. Okay, they react in a specific ratio. So And honestly, if we were European, or it's becoming more and more useful here. Instead of saying a cup of flour, we would say grams of flour. And that would really help us understand stoichiometry a little bit better, but we don't do that. So anyway, we have given 4.55 moles. We're trying to find grams of that titanium 4 oxide. If we think about our island diagram again, we're starting with carbon, we're trying to go to the TiO2. We're starting with moles of carbon, so we're starting in the same spot, but now we're trying to go to grams of titanium. So that tells us we're going a little bit further on the island. We can't get from moles to grams in one single step. We have to go, that's a really slow movement. We have to go first to the moles of titanium 4 oxide, then we can get to grams. So now we've thought through, we've made a plan, we know exactly kind of what we want to do, so then we can set it up. Okay, what it is that we're trying to determine, what we know, set up your conversion factors. Again, moles of carbon is what we're trying to get rid of. Moles of titanium 4 oxide is what we're trying to go to. The mole to mole ratio comes from the coefficients. The moles cancel out, we're left with moles of TiO2. We can set up our next conversion factor where we're going from moles to grams, because that's our second step on our island. The moles of TiO2 go away, we're left with grams of TiO2. That allows us to do the math, punch it in your calculator, round to the correct number of sig figs, 1, 2, 3. The answer is 242 when it comes to looking at that final answer. All right, so the last question that's on there talks about, or gives you a problem, and I'm going to let you work on that independently, and then we'll come back and see if you can do it. But the problem, what volume of hydrogen gas is liberated at STP if 50 grams of zinc react with excess hydrochloric acid? I'll give you a hint, and that one of the products is not listed, but it's a single replacement reaction. Okay, so stop the video, see if you can do that last problem, and then we'll come back and see how we did. Alright, so coming back from that last problem, you should have gotten this as your chemical equation. This is the first step. Chemical equations balance is the first step. That's really important. So you have zinc plus 2 hydrochloric acids make hydrogen and zinc chloride. At that point, you can then look at your problem and solve for it. So what volume of hydrogen gas is liberated? That tells you it's a product. If 50 grams of zinc reacts with excess hydrochloric acid, that tells you got those two products. That zinc chloride was your mysterious, we're not really sure what other product is there, but we know it's a single replacement reaction. So then we have to set up our unit conversions or our dimensional analysis to do the stoichiometry component. 50 grams divided by the molar mass. Nice little mole ratio, which this happens to be a 1-to-1. Then because we're looking at volume, this is our 22.4. When we think about our island diagram, we're going to a different location, and that's per 1 mole. So we do all the math. 17.1227 is our calculated answer. When we go back and look at 50 grams, this was a really stinky balance. It only told us really for sure that we had about 50, which tells us that we can only be as precise as that allows us to with 1 sig fig. And so we can make about 20 liters of hydrogen from that, because we're not really sure if we have 50, 49, somewhere in there, it's around 50, close enough. And that would be if we're not really trying to be very precise with that. So hopefully you got those answers, were able to look through that and understand that to the best of your ability. Here we go. That's all I got, because that's the basics for this week. Next week, we're going to start looking at a few more details that can give us some more things we can do with stoichiometry. But first, we just want to make sure you can get the unit conversions down pat. When it comes to the rest of this, you have a whole nother front and back fun little worksheet. Ta-da! It looks like this. Yeah. Most of the equations are there for you. Some of them I took off because I knew that you were smart enough to figure them out. And so those are there. The answer key is there, but it's just the answer. So I didn't get through all the problems, actually working all of them out. But it does give you the final answer. So sub does have that. So you have that information at least as you're working through them. Knowing that when it comes to some of the rounding things, maybe 1 or 2 decimals off, depending on which molar masses are used for that. So just think through that as you're going through those problems. The more you do, the better. It just is what it is with regards to practice. You got the rest of class to work on that. And hopefully, fingers crossed, prayers going up, that I'll be able to see you live and in person next week. So good luck. Enjoy trying to get your brain to work a little bit more as you work on stoichiometry for this fun Friday, the last Friday of January. Can you believe it? It's almost February. Missed y'all. Enjoyed seeing a few of you on Monday when I did lab makeups. We're getting there slowly but surely. So enjoy doing the rest of these. I know that's really a bad way to say that, but suffer through doing the rest of these as you practice and learn a little bit more about stoichiometry. Until next time. Oh, that was really bad.